All right, everyone, shall we get going? I just wanted to do two things before Ann took over on the next section. So first thing is there was a I actually did misorder something on the for the values of the viscous flow laws. And so I wanted to cover that quickly. And then later today or tomorrow, I will update the sort of the GitHub repository with the parameter file itself. So, so that you have the corrected version of that there, or you can change it on the screen. So the incorrect ordering was this. What I did is I actually I did not put the background material first. So then these values would represent the background. It's the same as the values we supplied to the mantle in the last series of columns. And I had put this column third instead of first for the background. The reason that I ended up not affecting the solution is because we're not really using the background in this case. Yeah, and so then there are compositional fields defining all of the model domains. So for the upper crust, lower crust, the mantle, they all have compositional fields covering that. And so if you run for 1 or 5 million years, the background is only going to have no or minimal influence. So the correct thing to do would be to take these values right here, 6.52 e minus 16, 3.5, 533, and 18 minus 6, which were originally in the third column, move them to the first column. And so then after that, these values for the non-initial plastic strain and plastic strain come after that. So I can retroactively change that, but this is a very good reminder that everyone makes mistakes, and don't do things in a hurried fashion. Don't change things in a hurried fashion, especially if you're going to present them in the next few days. But then this is also, and it's also a good reminder that oftentimes before I submit large 3D jobs or even 2D jobs, I do multiple runs through the parameter file to make sure everything in order. In this case, I missed something. It does happen, but definitely check your parameter files, of course, carefully before you submit and review them multiple times. And even better, have someone else review them for you as well. Any questions about that? And what I will quickly do is just share my screen one more time quickly before I turn it over to Ann, just to look at the look at the model results. So this is showing the non-initial plastic strain in my model after 1 million years. You could visualize something like the strain rate as well. And then this is very similar to the images I showed right here. And so then in this case, you actually have slightly different patterns. So Gary actually brought this out in the chat. And the final values of the deformation field you get, so the exact faulting patterns and the exact distribution of the non-initial plastic strain is actually going to be different than the model I showed, simply because when you randomize the initial plastic strain field at the beginning of the model, every time you do that, you're going to get a slightly different answer. So that, and so in that sense, what it means is that you run the same model twice with the same parameter file, and you're not going to get the same solution each time. That's actually a really important point. I should have covered that in the presentation. But my philosophy is that the overall characteristic patterns of deformation you get. So then if you were to measure the maximum amount of plastic strain or the number of faults, it doesn't matter if your initial conditions are slightly different with plastic strain, the overall patterns you should get each time are the same. And you can actually do that experiment. I've done that experiment in 3D. So you start out with different initial conditions for the randomized plastic strain. You run multiple series of models, and then you quantify the faulting patterns in some fashion, and you end up getting the exact same overall statistics or quantitative measurements for the fault network as a whole. So, yeah. And so, Gary, I think that probably answers your question as to why you had a different non-initial plastic strain field than the one I showed. It's because the initial conditions, the randomization, is different every time you run the parameter file. So at that point, I will stop sharing, and maybe are there any questions we should answer, or should Ann, should we turn it over to you at this point?
Yeah, I think we can. I think all the questions are answered. Yeah. Yeah, so we have half an hour left before we should start the discussion. So I don't think I can finish my whole presentation today, but we will just continue in the morning tomorrow. So let me just share my screen. right. Does that look okay? I can't see you guys.
Yep.
All
Paper
right,
looks
I
good.
saw a thumbs up. Good. Yeah, so this is the third part of the lithospheric deformation session, and it's an example that considers a brittle thrust wedge. Now, okay, because this model will take about 15 minutes to run, at least that's how long it took on my machine, with 2 processes, it would be great if you guys could start the model run before I discuss the input file and the setup, etc. So if you probably still are in the right tutorial directory, so you can just start to run the model with MPI run minus NP2 and then the aspect release version and the brittle thrust wedge PRM file. And I will wait a bit. I will not switch over to my virtual machine just to avoid problems. So I will also discuss the input file from the PowerPoint. I have all the parameters in there, just like John. So I'll just wait a little bit until everybody has a chance to start the model. Can I look at the chat now? Let's see. Yeah. Okay. So I don't see any problems with running the model in the chat. So I will continue with discussing what we're actually running. So just to get back to our schematic cross-section of plate tectonics, again, we're going to look at compressional crustal wedges today. So think of fold and thrust belts and accretionary wedges that form by off-scraping of sediments and crustal material from a lower plate, and then depositing these in foreland of an origin or at a subduction zone trench. And there are several theories that describe the behavior of the crustal material in such a wedge. And one of them is the critical taper theory. And it basically means if you have some material that is pushed along by a backstop, or in this case, by a bunch of cows on a bulldozer, this material will build up and build up until it reaches a critical angle, and this is the critical taper, and that's the angle that this toe of the wedge here makes, and it's the sum of the alpha angle, which is the angle of the surface, the slope of the surface, and the angle beta, which is the slope of the basal fold. And once it reaches this critical taper, if there's no new material being added, the wedge just is translated along the basal fold, and otherwise it keeps growing similarly. So it's just magnified. So analog experiments have done this kind of setup a lot, and they have shown differences in the results, and also numerical models of crustal deformation can show significant differences. And therefore, in 2016, Bouter et al. Did a tremendous benchmark effort to try and quantify the differences and also to explain them. So they collaborated with people with 11 different numerical codes, 15 analog labs, and they did 3 experiments. So the first experiment is just a translation of such a stable wedge, so there should be no internal deformation, while the second and the third consider a subcritical wedge, so it's not at the critical taper yet, that then undergoes deformation towards that critical taper. And today, we're just going to focus on the second model. And below, I put in a little teaser from the results of the paper. This is done with the code Pitatin. And you can see that there are 3 crustal sand layers, 3 sand layers that are being pushed from the right side. and fold and thrust belts form, so pop-up structures form and lead to shortening of the domain. I just wanted to highlight this modified word that I put in here because to make this model run on a virtual machine with two processes within reasonable time, I had to modify the original setup of the benchmark. So in the end, I will also show high resolution results of the actual benchmark, but what you will be running is a simplified version. So before we saw the 3 layers, but to actually run this experiment in Aspect, we need several other compositions. So this is what the setup looks like. So in green, we have 3 sand layers. There's quartz sand at the bottom and the top, and then corundum sand. Don't ask me what that is, in between. And these are brittle materials, so they have to follow a brittle criterion. It's non-associative flow, so dilatation is 0, but we do include strain softening. Then on the right in orange, there's this strong mobile wall that's being pushed in, and that is driving the deformation. And then the white layers in between are boundary layers that provide the frictional boundary. So we don't prescribe forces, we use these two thin layers with different properties from the sand layers. And then to allow for the buildup of topography, we don't use a free surface because in this case, the distortion is too great, the distortion of the mesh elements, but we use a sticky air, and it has to be pretty thick compared to the rest of the model to avoid any boundary effects. So in terms of boundary conditions for velocity and stress, as I said before, we push the mobile wall in from the right at a velocity of 2.5 centimeters per year, while we fix the y component of the velocity. Velocity is fixed along the bottom of the domain, it's free slip on the left, and then the surface is left open because we push material in from the right, so we have to conserve mass, or volume in this case, and an equivalent amount of what's being pushed in is going out through the surface. So that's set to 0 stress, but the velocity is left free, so stuff can move out. Yeah, I think that's all I want to say. So the density of the sticky air is 0, 0 again, and let's just see how that translates to a setup in the parameter file. So like before, you can open the input file with VI or leafbed or whatever you want to use, but I have put all the parameters on the screen so you can also just watch the presentation. And if you want to have a look at the original file, then this can be found in the Aspect benchmarks folder, where there is a low resolution and a high resolution version of the original experiment. So at the top of the file, we will have the global parameters. So again, it's 2D. We set use years and output instead of second to false. So the unit of time is seconds, and this number, so 14,400 seconds, corresponds to 10 centimeters of compression. Yeah, and then we use pressure normalization at the surface so that the average of pressure is 0 at the top. Then we get to the solver settings, and because viscosity depends on solution variables, pressure and velocity, we need to iterate on the solution, and we will not use the Newton-Stokes, but the iterated Stokes solver for this. And the amount of nonlinear iterations is controlled by the nonlinear tolerance and the maximum number of nonlinear iterations. Then the Stokes solvers themselves are controlled by the linear solver tolerance, the number of cheap Stokes solver steps, which the default is 200, but I just wanted to point this out. So this is a poorer but cheaper preconditioner for the GMRS solver. And the more complicated your viscoplastic models become, the less useful this is. But here it still helps to reduce computational costs. And then the GMRS solver restart length is changed from 50 to 200 so that we take more of the solver history into account. And this helps if you have highly localized viscosity jumps. So I just wanted to like visually represent the nonlinear iterations and the Stokes iterations or the Stokes solves one more time in combination with updating the viscosity. So within a time step, we do several nonlinear iterations. And within a nonlinear iteration in the material model, we calculate an effective viscous viscosity. So this can include dislocation or diffusion creep. Then we use this to predict a viscous stress, sigma V. And we use the pressure, cohesion, and the friction angle to compute the plastic yield strength. And then we compare the two. And when the viscous stress is larger than the yield strength, we rescale the viscosity and return this effective viscoplastic viscosity. If the yield strength is larger than the viscous stress, then we return the viscous viscosity. And with this viscosity, we solve the Stokes equations, we get an updated pressure and velocity, and then we go again. So we update the viscosity, compute, so solve the equations, get a new pressure and velocity, and go again. And we exit this loop based on whether we meet a certain tolerance or a maximum number of iterations. So to translate that to the input parameters we saw in the input file, we control the Stokes solves with the linear solver tolerance, the number of cheap Stokes solver steps, and the restart length. And we control this outer loop of nonlinear iterations with the nonlinear tolerance and the max nonlinear solver iterations. Okay, the second subsection that we come to is the discretization. So again, temperature plays no role in this model, so we decrease the polynomial degree from 2 to 1. We use the discontinuous discretization for composition, so this allows us to not use continuous shape functions, but actually have discontinuities at the edges of the elements, the faces of the elements, and that helps us to preserve the interfaces between the fields better, so to have sharper interfaces. As you remember, we have this very thin boundary layer, so it's important that that remains intact. And then we can apply global limiter. John mentioned this before. And I will just highlight that normally fields, if they represent materials like lithologies, they will stay between 0 and 1. But if they represent strain, which it does in this case, strain can keep growing, right, over time. So we set it to this high number so that we won't limit it in any way. And if you're interested in this, just follow the link to this paper, Gary's paper. But I just picked one figure from the paper just to show you the difference when this square block is sinking through this blue medium. Over time, it will deform and become sort of a jellyfish. But you can see that the boundary is way sharper for the discontinuous Galerking method than for the standard method. Okay. Well, I think by now you understand that the geometry model is a box, but this time it's a very small box. It's 36 by 8 centimeters. And I just want to point out how amazing that is that we can model the whole planet or just do like mimic an analog sandbox experiment. And again, we set some repetitions to get a nice 1-to-1 aspect ratio of the mesh cells. And then we get to the important part, the compositional fields. So there are 5 fields. So there's the quartz sand layer, the sea sand, and just this quartz sand represents 2 layers. I just wanted to point that out. So it's 1 field, but it's 2 layers already, 2 separate layers. Then there's the middle sand layer, the boundary layers, the block. This is the mobile wall that's being pushed in. And then there's a field called total strain. Yeah. you just have to believe me that these functions implement the initial conditions I showed in the setup figure. But it's one nifty little trick that I wanted to show you is that if the lines get too long, you can always break your expression with these backslashes. And also I set the total strain to 0 because we want to start with pristine layers for the sand. Yes, because we have material coming in through the right boundary, we want to fix the composition on this boundary to the initial composition, which practically means that there's only mobile wall material coming in and a little bit of boundary material at the bottom. In terms of temperature, we don't have to spend much time there. It's not important for this model, so it's set to the same value of 20 degrees Celsius everywhere. And again, we fix the temperature through the right boundary because we have inflow there. Then the velocity and stress boundary conditions. There's a lot going on here, but let's start here. So we fix the velocity at the bottom to 0. Then the left boundary is free slip, so tangential velocity only. And then we prescribe the velocity on the right boundary. And we do that with this function, and just put that graphically. We prescribe a velocity of minus 2.5 on most of the boundary, but then it tapers to 0 because the velocity is set to 0 at the bottom boundary. Gradual changes are always good. Also note that because we set the use years instead of seconds in the output to false, this is interpreted in meters per second. So I use these scalars, centimeter and hour, to go from centimeters per hour to meters per second. Then to have the sticky air be able to move out through the surface, I set the top boundary to 0 traction so that material is free to leave the domain. Yes, then the material model, the thing that stands out before we go to the actual viscoplastic material model is the material averaging parameter that is set to harmonic average. And this means that during the assembly, we average the material properties over the mesh cell. So we come up with one viscosity value and one density value, for example. And this is discussed in a paper by Timo, René, Juliane in 2017. And what I want you to take away from this figure is that if we don't use this averaging, but you have strong viscosity contrast, this can lead to high oscillations, peaks in the pressure. So minimum and maximum pressure here is 45 and 40, minus 45, plus 45. Well, if we use this averaging, we reduce these peaks strongly. And bonus, it also reduces the solver time greatly. Yeah, and I have the link to the paper if you're interested. So then for the viscoplastic parameters, I won't go through them all, but I will highlight that the minimum and maximum viscosity are quite different from what we are used to, I guess, till now, because we're doing this sandbox scale model or with sandbox materials. And I also wanted to point out that some parameters can be specified for each composition, but they don't have to. So for example, the heat capacity, here we see one value. That means aspect will use the same value for all fields, but you could also write 6 values here, 6 different values, or 6 the same for if you want to. Yeah, but you always have to supply one extra value because of this background field that is assumed to be the first field. And then we average the compositions, the contributions of the compositions to the viscosity harmonically. Then we set the viscous flow law to dislocation, but actually we don't want dislocation creep to happen. So we manipulate the parameters to let them provide constant viscosities. So activation energy and volumes are set to 0, stress exponent is 1, and then we only have these prefactors that determine the uniform linear viscosity. So basically 1 over this value is the viscosity that we will get. Then plastic parameters, these are modified by the strain weakening mechanism. So in the previous PRM, John showed that we used a plastic strain, and now we will use the total strain. And on the interval of 0.5 to 1, we will weaken the friction angle with this factor. So if you want to look at it this way, if you have strain on the horizontal axis and the friction angle on the vertical axis, between the start and the end of the interval, the friction angle will weaken from the original value to the value F times the original friction angle, with F being this friction strain weakening factor. So 0.861 for the quartz sand. And the last section I wanted to show is the mesh refinement subsection. So we have 2 levels of mesh refinement, and we both coarsen and refine the mesh over time, actually every 2 time steps, every second time step. And then for the first initial refinement, so at T0, we skip solving because our resolution is not high enough to resolve the boundary layers anyway. So let's not waste time in trying to solve. However, we cannot skip setting up the initial conditions because our mesh refinement is based on density, amongst others, and density is based on temperature and composition. So we need to know what the initial conditions are. And then for the minimum refinement function and the maximum refinement function, there's a lot of stuff going on in the slide, but I want you to take away that I use a function to specify what the maximum and minimum level of refinement should be in an area, in a specific point at a specific time. So I make this actually time dependent. So because we have this wall moving in, so this boundary layer between the sticky air and the sand and the mobile wall is moving in, I want the mesh refinement to follow this boundary layer. But I don't care so much about the resolution in the mobile wall, so the strong block that's moving in. So I'm coarsening the mesh in that area. You will see that once you've run the model. Okay, let's see. We have some minutes left. So you will have some results. Your run might not be finished, but you will have some results that you can look at. So I suggest you open ParaView and load the solution file. And then to create this figure, for example, this is halfway through the model run, I actually cut off all the stuff that we're not interested in. So the sticky air and the mobile wall block. So just to leave the sand layers. And I did this by using the calculator filter to sum Q sand and C sand, and then applying a threshold filter on top of this with a minimum value of 0.5. And this leaves out all the other fields because they are, because for all the location of the other fields, Q sand and C sand are not higher than 0.5. And then if you want to see these nice layers, you can select the density parameter to see them. So I suggest you investigate the results, maybe try to make some snapshots. So that's done by going to File and then Save Screenshot. And you can also have a look at the strain and the strain rate over time, because these tell us which folds have been active, that would be the strain, and the strain rate would tell you which folds are currently active, so you can see if there's a difference there. And then that is probably a good time to stop talking for me, because then you can investigate these results and we can see what we want to do about the discussion next.
I imagine there will be lots of questions in the discussion. The chat's been very active, so there's a lot of different topics we could go over. Do we want to go through like 10 minutes of question now before we do a break? Or are there any questions you would like Anne or myself to cover about any of the material from today?
So are there questions about this particular model?
Not to say in general, but
Or...
Gary's actually asking if you can demonstrate the calculator filter.
Let me try. I'll have to stop sharing first. And then share again. Yes, there we go. Okay, so we're in PowerView. I have my solution PVD right here. Yes. Okay. Calculator filter. That is this thing on the left. You can either like click on the symbol or go to filters and then search, for example, calculator. Well, it won't because I'm already in the calculator, but you can find it there. And then we will want to add the scalar Q sand plus C sand. Apply. Error messages, ignore. And then we want to add the threshold filter. That's this little T-shaped thing in a box. And set the minimum to 0.5. Apply. Yes. And then we set, instead of result, we use density and rescale. There we go. I hope that answers your question. Yeah, I'll stop sharing. All right. Other questions in the chat?
There was a long discussion about going between 2D and 3D models. What's the trade-offs between accuracy and using compositional fields and computing time using, let's say, DG versus particles? And the conclusion and sort of the answer Wolfgang and I gave is it depends a lot, and we're still in the process of figuring out these things out, exactly what the trade-off, what the best method is for things like long-term subduction or extension in 3D, and that there's a lot of trade-offs. Does that seem like a reasonable summary?
Yes. I mean, it depends on many things, including the number of materials you want to model. Yeah, so we ran.
Can you maybe summarize the behavior? Like, what is different about using a lot of compositional fields versus using particles to track these materials? Why would I, like, which one would be better if I just have one compositional field? Which one may be better if I have 100? Why is there a difference? Why do we not know at the moment?
I think it has to do with the memory requirements for the particles that become a limitation at some point.
Yeah. So that's one thing. And John, we talked about the time that's needed for many compositional fields, right?
Yeah, especially with DG. I'm not, Timur or Wolfgang or you, Renee, might know a bit better, but so I recently ran a bunch of models in 3D using DG, and it gave much sharper interfaces, but then there was a significant trade-off with the computational time spent actually assembling the compositional fields.
Yeah.
And so then there's no easy answer. I mean, my best advice would be to try a lot of things in 2D and slowly start building up to low resolution 3D models and do a lot of simple tests just for a couple time steps maybe to see how these different things are trading off in the timing. versus the, like the resolution. It's really hard. It's hard for everyone.
So the basic difference would therefore be that if you add additional compositional fields, with every field that you add another equation that has to be solved. And so the time that you spend, and the solution of this equation doesn't actually take much time. It's the advection diffusion equation that's very cheap to solve. But you need to assemble this equation, and assembling the equation takes actually longer than solving the equation. Every time you add a new compositional field, you add another assembly that you have to do. While with the particles, you need a lot of particles in 3D to get an accurate solution. But you only need to add this cost once, which means, and then you can apply, you can attach many properties to these particles, and you still need to interpolate these properties from the particles to the finite element grid, but this is relatively cheap compared to advecting these particles over time and updating the properties of the particles over time. So if you have many compositional fields, then using the particles can actually be faster. If you have just one compositional field, then having just one compositional field is likely faster. And somewhere in between there is a trade-off between the two methods. But then there are other problems, like the artificial diffusion that you see in compositional fields, which is reduced if you use the DG fields. But the DG fields are more expensive to assemble. So you have, again, this trade-off between artificial diffusion and runtime. And with particles, you have to worry about the distribution of the particles. So particles tend to cluster over time. And you need to avoid that with some mechanism that removes particles in areas where there are too many, and you have to add particles in cells that are empty. And so the two numerical methods have different advantages and disadvantages, and it's hard to tell beforehand which one works better for a given problem. So I guess that's kind of a summary of the particle versus field discussion.
I would say another disadvantage of particles for the type of models we've shown is that you, like in the example Anne showed, we're effectively using a sticky air method where we're using a low density and low viscosity layer to approximate a free surface. And when you add that in, oftentimes I've noticed in extension models, I haven't put any of these into aspect repository yet because I'm still trying to tweak them to optimize things, but you notice some other weird diffusion of, say, plastic strain across the interface, and I needed to use 200 to 300 particles to remove a very large number of particles in 2D to remove those effects. And so then I think ideally maybe long-term is with some of the higher order particle interpolation methods combined with the free surface. I think I'm sort of hopeful that will be a long-term, the best long-term optimal method, but we'll have to see with more testing in the next couple months.
Yeah, so for this model that I was actually discussing now, I also set up the same model, but with particles and not DG. And that was slightly slower, but not significantly slower. But the diffusion of the boundary layer is way less than with the fields. So, but I personally have not experimented a lot with the particles, so I cannot say how it would affect my models. But we have, for example, our PhD, Derek, has tried the particles in 2D riff models. Yeah, and there, time-wise, it was more expensive, and the improvement that we got was not that much, so we switched back to fields. So I think it's really setup dependent, yeah. And we cannot give like one rule.
I will say one advantage of the sticky air layer is that, and using particles, is that then you can use the GMG solver, and that dramatically speeds up the slope solve time. So then when in an extension model I tried, I think Wolfgang showed it on the first day, that actually used a sticky air layer. And there, using the particles plus the GMG solver, it actually was a speed up compared to using the free surface in the compositional field after he implemented the GMG solver. So again,
this is something that may be confusing to many participants because we haven't discussed the internal Stokes solver of Aspect a lot during the tutorial so far. And I don't think we will actually discuss it a lot, right? But maybe just quickly, there are some recent developments in the solver that actually solves the Stokes equation in Aspect that can significantly speed up the solver if you run a setup that is supported by this solver. Unfortunately, it does not support the free surface, for example, at the moment. We will likely switch to the solver as a default at some point. It is not yet the default solver in the version that you are using in the virtual machine, but you can already switch to it. And if there is interest, then we could discuss that in one of the discussion sessions. But as I said, it's not going to work for every setup, but ideally it can speed up the runtime significantly compared to what is currently in the virtual machine. And that was work by Timo Heister and his PhD student, Konrad.